Alex Coomans, a software engineer on the infrastructure team at Persona. For the past several years, I've been part of the team responsible for scaling and evolving the architecture behind our identity platform. These days, I help design and maintain the globally distributed multi-cluster Kubernetes setup we operate today. Although I wasn't around for the very first commits by our founders, Rick and Charles, I know the challenges they faced, like many of y'all, in taking this from an initial idea to a fully functional Rails application and product. But before we dive in, let me first give you a bit of context on who we are at Persona and the kind of problems our platform is built to solve. Persona is an all-in-one identity platform. Think of onboarding, compliance, fraud prevention. We power the behind-the-scenes workflows that ensure individuals and businesses are who they say they are. Our platform's flexibility is what makes us stand out and applicable to so many different use cases. We work with customers across a wide range of industries: fintech, healthcare, marketplaces, crypto, travel, government, and more. And each one has their own unique set of compliance requirements, user flows, risk tolerances, and regional regulations. That means almost every customer uses our platform in a slightly different way. And as such, we've had to architect for adaptability, a choice that has influenced almost every part of our stack. And with that context, let's rewind the clock and walk through how our Rails architecture has had to evolve to support that level of flexibility, scale, and diversity of use. Persona started the same way so many other companies have, with an idea and a command, one we've all used to bootstrap our grand visions, but that simple command comes with a plethora of options behind the scenes, some of which are innocuous early on, but carry deep implications for how your system will scale, evolve, and operate years down the line. In our case, we launched on Google App Engine, which gave us just enough infrastructure to move fast without worrying too much about provisioning or deployments. If you're not familiar, it's a fully managed platform that abstracts away most of the operational complexity, similar to Heroku or a lightweight subset of what Kubernetes offers out of the box. We started on Rails 5.2, well into the maturity of many Rails features, and given that was a little over 7 years ago, here's a refresher on some of the major features that launched then. We'll come back to a few of these and how we manage scaling with them. But first, let's talk about one that hit early and often, the asset pipeline. Let's time travel back to 2010, a time when jQuery was your best friend. These are screenshots of some actual code I wrote in a Rails 2.3 application. You'd manually include JavaScript files in your templates, and yes, your actual JavaScript logic would often live right in your Vue templates, tightly coupled to the markup it was enhancing, a pattern that's become back in style. In 2011, Rails 3.1 introduced the integrated asset pipeline, and it was a game changer. It gave us a structured way to organize, bundle, and minify assets. In the lower example, we include a file named usertabs.js to be executed on the page. But what happens when that file changes? We generally want browsers to cache script content for performance reasons. But if the file name stays the same, users might keep getting the old version even after we've deployed new code. The asset pipeline solved this with fingerprinting, appending a unique hash to the file name. With a new file name, the browser requests the file, giving us the best of both worlds: long-term caching when things don't change, and instant updates when they do. The integrated asset pipeline has evolved significantly, but it originally meant sprockets with defaults of CoffeeScript and Sass, languages that compile to JavaScript and CSS, respectively. And of course, we already saw a healthy dose of jQuery, which was the go-to solution for modern front-end interactivity at the time. Options for what we now consider a full-fledged front-end framework were limited. The first release of what would eventually become Ember came later in 2011, led by Yehuda Katz, a member of the Rails core team. The front-end landscape quickly exploded, though, in the following years. New frameworks, modern JavaScript features, many of which were influences from CoffeeScript, richer UIs, and rising expectations from users and product teams alike. Ember, along with other fledgling frameworks like AngularJS and React, shifted more of the UI into the browser. And with that, Rails increasingly took on the role of an API provider rather than a full-page renderer. With that explosion, the other major responsibility left on Rails was coordinating with a front-end build system in the asset pipeline. That resulted in the Webpacker gem, an NPM package that was added as an option with Rails 5.1 in 2016 and became the default with Rails 6.0 in 2019. Persona started squarely in the middle of that evolution, starting with React and TypeScript through Webpacker. Webpacker set out to connect Rails with modern front-end tooling, and for a while it did. But as complexity grew, we started to see the cost: hard to debug configurations, slow feedback loops, and lagging support for emerging tools. The breakneck pace of front-end innovation made it nearly impossible for Webpacker to keep up, turning what was meant to be a bridge into a constant game of catch-up. And all the while struggling to reconcile Rails' opinionated defaults and focus on quick implementation with the extensibility and configurability of modern build systems. In the end, we've moved from Webpacker to Shakapacker, and now we've adopted Vite, a modern native JavaScript build tool that's fast, flexible, and designed for today's front-end workflows. And that's been a recurring theme for us. Rails gives you great defaults, but you're not locked in. When the built-in tools no longer fit your scale, your team, or your workflows, it's okay to step outside the box and bring in what works. As we started to grow, we started to hit the natural limits of Google App Engine. It had served us well during our early days, giving us speed and simplicity when we needed it most. But eventually, the trade-offs became too hard to ignore. We needed more flexibility around how we structured services, or really just to easily deploy multiple services at all. To set the stage, picture what scaling looked like in our early days. A service would spike, an alert would fire, and someone would jump in and manually scale things up or down. This is a slide from one of our all-hands meetings in April of 2020, showing 5 straight days of manual scaling operations, scaling services up and down, sometimes multiple times a day, just to keep things running smoothly. That moment, looking at this slide, and realizing how much of our energy was going into keeping just the lights on, it was a clear signal. It was time to grow into something more sustainable. So we knew we had to move off of Google App Engine, but what options were actually viable? The most basic option would be to run raw virtual machines, maybe wrapped in Terraform and managed with Ansible or some other homegrown tooling. Technically, that probably would have worked, but it would have meant taking on a ton of operational complexity ourselves, solving problems that much more mature tools had already solved. Another option was to leave GCP entirely and move to AWS or Azure for a different platform as a service. But realistically, that wouldn't have guaranteed a solution to any of our core issues, and it would have added a massive migration on top of an already complex problem. After weighing the options, we decided on something that gave us the control we needed without starting from scratch: Kubernetes via GKE. GKE is Google Cloud's managed Kubernetes offering. It handles the heavy lifting of cluster provisioning, upgrades, and node management while still giving us substantial operational control. Making the jump from Google App Engine to Kubernetes wasn't just a change in deployment systems. It was a fundamental shift in how we thought about infrastructure. App Engine handled most of the heavy lifting for us: provisioning, scaling, networking, even deployment, all abstracted behind a few CLI commands. But that simplicity came at the cost of control. Migrating Kubernetes gave us flexibility, observability, and granular control, but required a maturity leap in tooling and practices because it asked us to take ownership of every part of the stack. From networking and observability to deploy workflows and access control, we suddenly had a lot more flexibility and a lot more responsibility. Let's take a side-by-side look at how each platform handled the key components of our infrastructure and what changed when we made the switch. On App Engine, you simply push code and Google takes care of the compute. No servers to provision or orchestration tools to configure. In Kubernetes, you manage the full lifecycle of containers and the nodes they run on. Depending on the cloud vendor, or on-prem, that could vary between relatively easy with managed services like EKS and GKE to fully hands-on if you're running your own control plane and node infrastructure. GAE also doesn't support GPUs or other specialized compute resources, which have become increasingly common as modern workloads have exploded in popularity and utility. And those now power critical parts of Persona's platform, like document analysis, biometric matching, and real-time image processing. When it comes to controlling your application's scaling behavior, App Engine allows you to define targets for CPU utilization and concurrent requests, but that's about it. Kubernetes, on the other hand, gives you fine-grained control with the ability to look at both system and custom metrics, in addition to being able to scale both horizontally and vertically. It even supports custom scaling logic through integrations with external metrics APIs and other controllers, making it highly extensible, whether you're scaling based on queue depth, request latency, webhooks, or any other signal relevant to your application. As we alluded to earlier, this flexibility was a key driver in our migration to Kubernetes. App Engine's scaling model is heavily geared towards request response web traffic, and it didn't handle background job processing, like what we do with Sidekick, very well. We needed more control over how and when workers scaled, especially under our very bursty workloads, and Kubernetes gave us the tools to do that. I'll be honest though, our move to Kubernetes didn't immediately remove our manual scaling desires. It took time, experience, and a bit of patience to craft horizontal pod autoscalers that met our needs. But once we got there, it changed the game. The system finally started working with us, not waiting for us to catch up. Networking, like compute, is fully managed by App Engine. There are no load balancers to configure, unless you'd explicitly like to do so, and simply deploying your application gives you a publicly accessible endpoint out of the box. With Kubernetes, you're empowered with services, ingresses, gateways, and a host of related objects and configuration knobs. You can build complex load balancing strategies with traffic routed across multiple services, paths, or backends, all without leaving the Kubernetes ecosystem. But with that power comes responsibility. You now have to manage DNS, TLS, health checks, firewall rules, and more. All of which can add operational overhead if not carefully designed and properly configured. It's not uncommon to see deployments missing critical pieces, like readiness probes or ingress annotations, leading to flaky traffic routing, failed rollouts, or subtle production issues. App Engine makes observability effortless. Logs and metrics are automatically captured and integrated into Google Cloud's monitoring tools with minimal setup. It's simple, consistent, and good enough for many use cases right out of the box. In contrast, Kubernetes gives you a blank slate. You have the freedom to plug and manage observability platforms like Datadog or build out your own stack with tools like Prometheus. That freedom is powerful, but it also means you're responsible for wiring it all together, deciding what to measure, and making sure nothing falls through the cracks. So while the move to Kubernetes gave us the control and flexibility we needed to scale our infrastructure, it also came with new complexity that we had to learn to manage carefully. Our deployment infrastructure wasn't the only thing that had to evolve. As our usage grew, one of the next places we felt real pressure was in our database layer. As our product and customer base evolved, so did our data in volume, structure, and complexity. In mid-2022, we began sharding our application to address the growing pressure on our primary MySQL cluster, starting by adding a second shard in the same compute location. And just to keep things interesting, we kicked off work at the same time to add a third shard, this time in Europe, driven by data residency requirements that called for isolating customer data within specific jurisdictions. In the span of just 6 months, we went from one database and one Kubernetes cluster in one region to 3 shards across 2 regions and an additional Kubernetes cluster to support it all. Rather than relying upon a single database, we use a combination of MySQL and MongoDB as our primary data stores, along with Elasticsearch for search and indexing workloads, and Redis for caching, scikit queues, and other ephemeral data. Each of these systems brings its own strengths and its own operational challenges, especially in cloud-managed environments. Choosing the right one is only half the battle. Scaling, tuning, and managing them in production is where the real work begins. While MongoDB offers native support for sharding, making horizontal scaling more straightforward, MySQL posed a much harder challenge. Sharding our relational data meant untangling assumptions deeply buried in our application code and schema, and that's where we'll focus next. Rails has only recently started offering official support for sharding, but applications have been hacking around that limitation for years. Rails 6.0 added support for configurable database connections by model, allowing applications to route specific models, or even reads versus writes, to different database instances using the connects to and connected to APIs. This is effectively known as vertical sharding, where you split entire tables or domains across databases. One database might handle user data, another might handle payments or audit logs. It's relatively straightforward because the location of each type of data is fixed. You always know which database to query based on the model. Importantly, though, this laid the groundwork for what we typically think of when we say sharding, horizontal sharding. Splitting rows of the same table across multiple databases, each holding a different slice of the data, but sharing the same schema. Long awaited, Rails 6.1 introduced native horizontal sharding. It was finally, relatively, easy to support multiple shards of the same model in your application. When we set out to shard our MySQL cluster, we weren't starting with a clean slate. We were adapting a growing, rapidly changing Rails application to a pattern the framework had just recently begun to support. And as you can imagine, that came with its own set of surprises. Rails' connected to helper is an essential building block for sharding. It lets you swap the database connection on the fly based on context. Think of it like a railway system. Each shard is a different destination, and connected to is the track switch. Before the train, your request, job, or rake task leaves the station, you need to flip the switch to send it down the right track. If you forget or flip the wrong one, your data ends up at the wrong terminal, or worse, on a collision course with something else. And just like that, and just like in a real railway system, you can't expect the train to figure it out mid-route. This context has to be set up front. In practice, this means your code base needs to use that building block everywhere you're interacting with data. No small feat, even in a mid-sized Rails application. Threading shard context through an app isn't necessarily hard in isolated cases, but it requires discipline and consistency. For job processing, it's relatively straightforward since you've already looked up the shard by querying the record. In our case, we added a query parameter to the global IDs of objects passed to the jobs, which indicated the correct shard, allowing the job to reconnect to the right database when it runs. For web requests, though, it's a bit trickier. You're now forced to rethink what information is required to route a request, and make sure that shard context is both available and trustworthy by the time the controller code runs. Take a public API as an example. You're probably identifying requests with an API key. That becomes your routing key, the piece of context that tells you which shard the request should go to. But that's only half of the equation. You now need some kind of directory or lookup table, a centralized way to map that routing key, API key, object token, to the correct shard. Notice the find shard example in this example from our application. Without that layer of indirection, you're left hard coding assumptions into your app, and that just doesn't scale. And here's where things get even more interesting. That lookup table might need to scale far more than you'd initially expect. In many cases, you're supporting APIs with unchangeable contracts. Maybe they're embedded in physical hardware, IoT devices, or distributed SDKs in mobile apps that can't be easily updated. That means every request to your platform, even the very first one, needs to hit the right shard with no opportunity for client-side logic to help. As a result, what looks like a simple lookup turns into a high-throughput, low-latency critical code path, one that needs to be highly available, globally accessible, and fast enough to sit in front of any user-facing request. At Persona, we solve this by backing our lookup table with MongoDB, which makes it very easy to support globally distributed read replicas with minimal operational overhead. That allowed us to serve shard routing lookups close to the user, no matter where the request is processing. Because the routing logic sits in the critical path of almost every request, especially in our public or SDK-facing APIs, having that data available, fast and everywhere, was non-negotiable. As of last week, we had just over 1 billion entries in that lookup table. Long before we even needed to shard, we were already feeling the pressure of working with large MySQL tables. As usage grew, certain tables ballooned in size, and that brought a new class of problems. Slow queries, painful migrations, unpredictable query plans, and operational risk from even simple schema changes. And while sharding helps you scale horizontally, it doesn't eliminate those problems. In fact, it can make them even harder to manage. Now you're not just maintaining one large table, you're maintaining that same large table across multiple shards. Every schema change, every index tweak, and every performance fix now has to be repeated across n databases. Schema changes on large MySQL tables can be deceptively dangerous. By default, operations like add column, modify, or drop index can lock the table, block reads or writes, and introduce unexpected performance regressions, especially if that table is in the critical path. For a long time, tools like Percona's PT online schema change and the LHM, Large Hadron Migrator, originally open sourced by SoundCloud and now maintained by Shopify, have sought to bridge that gap. For extremely large tables, though, it can result in migrations taking weeks, potentially stalling the work of other engineers or changing query planning results and slowing down unrelated parts of your application. Recent versions of MySQL, particularly 8.0, support more instant DDL operations, like adding and removing some columns or modifying default values, without requiring full table rebuilds. That still leaves things like index creation requiring full rebuilds. So that's where access pattern design becomes essential. One of the biggest challenges with large MySQL tables is that small inefficiencies at scale really start to hurt. A missing index, a poorly chosen primary key, or an unexpected query plan might be invisible with 100,000 rows. But with 100 million, it becomes a problem you can't ignore. It's not enough to model your schema around the shape of your data. You have to model around how that data will be queried, filtered, and joined in real application usage. If you've worked with NoSQL systems like DynamoDB or MongoDB, this mindset may already be familiar, where you have to design your schema around your queries, not your entities. In relational databases, that kind of upfront thinking is often overlooked, partly because you can get away with it, especially early on, and it lets you build faster. But as tables grow and usage scales, those early shortcuts start turning into real pain. Large tables also introduce challenges when teams need to run backfills, not just because they take a long time, but because they can unintentionally impact performance. Depending on how the backfill is executed, it can evict hot pages from the MySQL buffer pool, alter index statistics, or disrupt caching behavior, all of which can degrade query performance in unpredictable ways. Of all the large tables at Persona. The top two are from a familiar Rails component. Active storage was introduced to simplify interactions with files stored in cloud object stores like S3 or GCS, and provides a flexible attachment system that makes it very easy to associate with any active record model. It's built around two main tables: blobs, which represent the actual files in the object store, and attachments, a polymorphic join table that connects those blobs to an application record. At Persona, these two tables represent the top 2 by row count in our application. Since each file is attached to exactly one record, their row counts are nearly identical at around 3.4 billion. That makes them the perfect storm. They're huge, they're hot, and they're hard to touch, which becomes especially painful when you need to backfill metadata, migrate attachments, or optimize access patterns. And modifying models outside of your application, whether or not they're Rails components or external gems, is particularly tricky. Given these challenges, we've started to migrating to Shrine, which takes a more lightweight, modular approach, using fields directly on individual records to track the file attachments instead of requiring a separate join model. Sometimes, though, it's the core of your system. It's not the core of your system that causes the most pain. It's the abstractions you thought you didn't need to think about. We've been talking a lot about MySQL, and that's intentional. It's the database powering many Rails applications. But many of these lessons aren't unique to MySQL. You'll encounter them with any relational database. At scale, every data store brings its own set of challenges, and we face them all. We've dealt with hot shards on MongoDB, fought through index tuning and cluster pressure on Elasticsearch, and even had to shard Redis to keep up with Sidekiq throughput. The reality is, no database stays easy forever. Once you're operating at scale, even the managed parts of your stack demand careful planning, constant tuning, and a good dose of humility. While I'd love to unpack all those war stories, we simply don't have time today. You might be wondering, though, where's the simplicity in all this? That leads me into what we're working on now, an intentional return to simplicity. You might be wondering why this slide says one Kubernetes cluster and one MySQL cluster. After everything we talked about, that probably sounds backwards. We didn't shrink. We didn't suddenly stop needing to scale. What we did was simplify. We took everything we learned, the patterns, the guardrails, the wins, the pain points, and restructured it into a single consolidated deployment model designed for reuse with strong tenancy boundaries and predictable growth curves. It's not a step backwards. It's a step of years of experience teaching us that for the way we scale, simplicity might be the only way to do it without losing your mind. This architectural shift is a project we call Stacks. The idea was simple. Instead of scattering complexity across multiple clusters, databases, and other systems, we defined a single, self-contained unit that could run our full platform. And then we replicate it again and again and again. In some ways, this architecture resembles what's often called single tenancy, where each customer gets their own isolated environment. In our case, though, it's a bit more nuanced. Each stack isn't necessarily tied to one customer. It's more like a self-contained runtime that can host many tenants, but with strong boundaries between the stacks themselves. So while we borrow some of the benefits of single tenancy, like isolation, blast radius reduction, and operational flexibility, we don't take on the overhead of spinning up a new environment for every single customer, essentially a middle ground. While the main components of each stack are isolated, including their own databases, there are still a few database-backed services that we share across all customers. Chief among them is the lookup table we discussed earlier, which routes the requests to the correct stack. We call these cores, centralized systems that power critical functionality across all our environments, while everything else remains stack-specific. Routing a request to the right stack isn't all that different than what we had to do with sharding. It has to be correct from the very beginning. Just like with database sharding, there's no room for ambiguity. Once a request hits our edge, we need to know exactly which stack should handle it. If we get it wrong, the request simply fails. So this isn't just a routing concern, it's a critical correctness boundary. Let's walk through a real-world example to see how all this comes together. Though just to be clear, we're pretending this is the actual map of all of our edge and main compute locations. The real one is a bit too dense and not nearly as slide-friendly, but this gives you the general idea, hopefully. Consider the green triangles to be our edge locations and the coral cans as our main compute. Say you were to make a request from here in Philadelphia. That request would get routed to the nearest edge location. That might be as close as down the street or a few hundred miles away. Kind of depends on how the internet's behaving that day. Let's say that happens to be in Virginia, a pretty short hop at light speed. To make stack routing work, we run code at the edge, as close to the user as possible. This layer inspects each incoming request and parses out the key routing metadata. Things like object tokens, API keys, sessions. We'll first attempt to look that key in a local cache. For things like API keys, where callers are typically isolated to 1 or 2 locations, we see a really high cache hit rate, which means we can route that request to the correct stack almost instantly. In the roughly 7% of the time that we miss, like for routing keys that have callers spread across many locations and don't frequently repeat, we'll query the lookup table in MongoDB. We have read replicas distributed across the globe, so we're able to make decisions in under 150 milliseconds for 95% of those cache hit miss requests. Now that we've determined where your request should go, we'll actually route it there. This time to a stack in Europe, where the request will be processed. All in, this approach allows us to introduce this architecture change with 0 modifications to customer implementations. No SDK updates, no endpoint changes, no new headers. Just a cleaner, more scalable backend infrastructure that works exactly the same from the outside. That kind of seamless evolution is hard to pull off, but when it works, it's one of the clearest signs that your abstractions are holding up. While these stories have been about how we managed the last 7 years, scaling Rails, taming complexity, and evolving our architecture, they're really about something bigger, and we've learned a few lessons along the way. Complexity is inevitable, but if you're intentional, you can choose where that complexity lives. Rails gives us great defaults, and we've embraced them, but we've also learned not to treat those defaults as constraints. Simplify where you can, scale where you must, and don't be afraid to step outside the box when necessary. I appreciate y'all joining me today to hear some of our war stories, and I hope that some of these lessons help you on your own journey scaling Rails, whether you're just starting out or deep in the trenches. On a final note, this is the Persona team we have at RailsConf this week. You'll be able to find us at the Persona booth back there above in the floor above in the Liberty Foyer or around at sessions. We'd love to chat with you. We are hiring. Thank you very much.